All right, so we're still in 9.3. This is just kind of a thought exercise more than anything else, not anything I would be real concerned about as far as the testing situation goes. But let's just suppose you run a series of hypothesis tests to see if the true population mean weight of 3 species of grasshoppers is significantly less than 0.454 grams. You take a random sample of 35 of each of these 3 species and run 3 different one-sided significance tests at an alpha level of 0.05. So we're testing this versus this. Suppose that the p-value for all 3 tests are as follows: 0.051, 0.049, 0.0003. So just kind of look at those p-values and kind of think a little bit. We're running at an alpha level of 0.05. So first of all, what conclusion would you make for each of these? Well, this is bigger than 0.05, so we would fail to reject. So we would conclude that the mean is, so we would fail to conclude that the mean is less than 0.054. Here, this is less, so we are going to reject the null, but it's close. And we conclude that it is less than 0.54. And this one is much smaller, so this is going to be reject also. Discuss the strength of evidence against the null in each test and why it's important for statisticians to report both the p-value and the conclusion. So the idea here on this one here is that you should kind of see that these two values are really, really close. This one was just barely not big enough, and this one was just barely big enough, small enough, I should say, in order to reject. But as far as the strength of the evidence goes, these are pretty much the same amount of strength. It's just one was on the wrong side of this arbitrary number, and the other one was on the right side. But the conclusions are completely different, right? Here, this one is overwhelming evidence. This is, a p-value this small means that, there's almost no way that the null hypothesis is true. And it's just the same conclusion as this one here. So I guess what I'm trying to say is if you just look at the conclusion, you might think that these two tests have the same results. Well, I guess they kind of do, but they certainly have a different amount of evidence. The sample gives different amounts of evidence against that null. And bottom line, statisticians want to see the p-value. If a statistician knows what they're doing, they see a p-value, they can make some own justifications about how much strength there is. Even if your p-value is 0.07, yeah, you're going to fail to reject, but is this some evidence? Yes, it is. You just didn't have enough, you just didn't reject. If you'd run the test again, maybe you will reject. Or maybe your power just wasn't enough. Maybe you should have increased the sample size just a little bit, and you would have rejected. You would have detected a difference. So anyway, confidence intervals and significance tests. Now this is something that you might see on a testing situation. As we mentioned before, confidence intervals may be used in place of significance tests. I would encourage you not to do it on your own. If I say run a significance test, please run a significance test. But in a multiple choice question, they might ask you to use a confidence interval to draw a conclusion to a hypothesis test. For proportions, confidence intervals are slightly different than the significance test. If you remember, when you do a hypothesis test, you use this formula for the standard deviation. And if you do a confidence interval, you use this formula for the standard deviation. Those are slightly different, or can be slightly different. And because of that, you could actually get a different test result if you use a confidence interval versus a significance test. But they're usually very close, so it usually doesn't matter. However, for means, you always use this formula. It's the same for confidence intervals and significance tests, so they are exactly the same. All right, so here's how we use confidence intervals to draw conclusions of a significance test. If you're doing a two-sided test with a null hypothesis of this and an alternate of not equal to, and you run it at a level alpha, let's just pretend alpha is 0.05 for the sake of argument here. So a significance test at a two-tailed significance test at an 0.5 level is equivalent to constructing a 1 minus alpha or 95% confidence interval and observing whether the hypothesized value is in the interval or not. If the hypothesized value is in the interval, then you fail to reject, and if it's not in the interval, then you reject the null. That's it. That's pretty straightforward, you know. I wish I had an example. I guess I got an example coming up here, but a one-sided though is going to be a little bit tricky. You got to be careful with a one-sided, because when we run a one-sided test, we're only looking at the area on one tail. But confidence intervals are always created with two tails. So if you want to run a one-tailed test with an alpha level of 0.5, then you need to run a confidence interval that has the area of 0.05 on the left tail, and therefore it's also going to have 0.5 on the right tail. So if you want an alpha level of 0.5, you got to pick a 90% confidence interval, not a 95. So if you're running a one-tailed at alpha, it is equivalent to constructing a 1 minus 2 alpha confidence interval. That's 1 minus 2 times 0.05. And then your conclusion is the same. If the hypothesized value is in the interval, fail to reject. If it's not in the interval, reject the null. All right, hopefully that kind of made sense. Let's just do an example. Suppose we wish to run a one-sample t-test for mu. We want to test this versus, actually I think this is a typo. Let's change this to a, it's just the wrong direction. I want to do a mu is greater than 80%. And you want to run it at an alpha level of 0.02. Several confidence intervals are given below. So we got a 95 confidence interval, 96, 98, and 99. Which conclusion would you draw to the one-sided test above? So just looking at this, our null is that it's 80. So this one does not have 80 in it. This one does not have 80 in it, but these two have 80 in it. So two of them are going to be, I'll give you one conclusion and two are going to give the other. The question is, which one should we look at? It's very common on a test for kids to just say, well, alpha value corresponds to 98%, right? Well, it would if it was a two-sided test, but this one is a one-sided test. So if I want to run a one-sided test less than, then I want my area to be 0.2 on this tail. That means if I do a confidence interval, if I want 0.02 on this tail, then I need to have 0.02 on both tails, and I need a 96% confidence interval. So we should not be looking at the 98, we should be looking at the 96. Do I have convincing evidence that at the 96% confidence level, that the mean is not 80? 80 is not in that interval, so I have convincing evidence that it's not. So I'm going to reject the null because 80 is not in the 96% confidence interval. Okay? All right. So we have one more test to talk about here. Just don't freak out here. For all practical purposes, it is exactly a one-sample t-test for a mean. It's just going to look and feel a little bit different, but it's basically, that's what it is. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals yields paired data. Paired data comes from a matched pairs design. Paired data is often analyzed as a single sample using the difference of the two observations. This is called a paired t-test or a matched pairs t-test. So this is going to be the name. This is kind of a special name, so you don't have to say one sample, whatever. You could just say paired t-test. So the null hypothesis is that the mean difference is equal to 0. against the alternate that it's greater than, less than, or not equal to. Your test statistic looks the same way. It just instead of x bar and s sub x, I'm putting in d bar and s sub d, where d is going to be the difference list. You'll see what I'm talking about here when we do an example. And you got n minus 1 degrees of freedom. As I said, it's basically a one sample t-test on the difference list. So that's it. Okay. How much do I got? Yeah, let's just do the next example and right, next video.